Exceptions to the octet rule. The octet rule is so nice and happy, but of course there's things that are exceptions. Well, one of the obvious exceptions is when you have an odd number of electrons. If you have an odd number of electrons, you can't possibly have 8 on each atom. It just doesn't work out. And so there are molecules and ions that have an odd number of electrons. These are called free radicals. They tend to be very unstable and reactive, and that's why you've probably heard of free radicals and they're not necessarily good for you, right? Because they tend to undergo a lot of reactions that your body doesn't necessarily like. So how do we do this? Let's look at NO, one of my favorite compounds, and draw a Lewis structure for NO. Right? So it's N and O. 5 valence electrons for nitrogen, 6 for oxygen, so it's a total of 11, right? Just the odd number tells us we're in trouble. So 2, 4, 6, 8, 10, 11. Okay, well, nobody has an octet. We can do better than that. Let's share a little more here. Nitrogen has an octet, oxygen doesn't. But we can't make everybody happy. We could, though, draw it a little differently and put the odd electron over here on the nitrogen and the 2 lone pairs on the oxygen. This molecule does exist. It's one of the bad things that's in air pollution, and the reason it's bad is it reacts with all kinds of junk. So what do? Lewis structure can't handle, Lewis theory can't handle this. We just draw the best we can, and we're going to use formal charges to help us with that. So let's look at the formal charges on these guys. Cutting the bonds in half. So here, nitrogen came in with 5. He's going to leave with 6. 5 minus 6 is -1. He has a -1 formal charge. Oxygen came in with 6. Is going to leave with 2, 4, 5. 6 minus 5 is +1. Down here, we've got nitrogen coming in with 5 and leaving with 5. So 0. Oxygen coming in with 6, leaving with 6, 0. Which is the better Lewis structure? The bottom one. So this is the best Lewis structure. Any questions?
Yes. What if a compound have an extra pair?
We'll find out what happens when you've got extra pairs of electrons. You know, what if you had so many electrons there that even with just single bonds, you've got too many? We'll come across that as well. It's a different exception to the octet rule. So odd electrons, incomplete octets. Some elements tend to form incomplete octets. We've already seen that hydrogen and helium only want a duet. There's a couple of other small ones that tend to be happy with fewer than 8. One of those is boron. So draw a Lewis structure for boron trifluoride. Okay, so here's boron, and fluorine is more electronegative, so we're going to definitely put those guys on the outside. I'm going to move over because I'm not going to have enough space there. Boron and fluorines. So valence electrons, how many valence electrons does boron have? 3. And we've got 3 fluorines, and they each have how many? 7. So 21 and 3 is 24. So we've got an even number, that's nice. So we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. What we've been doing, though, is we would say, well, boron doesn't have an octet. We need to share some more. So let's try that. So we'll take that pair of electrons and share. So now everybody's got an octet. But let's look at formal charges. What's the formal charge on this fluorine? 0. Plus 0. Good save. I like that. If we look at fluorine by itself, it has 7 valence electrons. What did I just show you? If fluorine makes 1 bond with something, it's probably going to have 0 formal charge. So this has got a 0 formal charge. That's got a 0 formal charge. This one does not have a 0 formal charge. Oh yeah, why not pink? Does pink show up? See that? Yeah. Pink and green. Reminds me of high school. What's the formal charge on this fluorine? Plus 1. It came in with 7. It's leaving with 6. So this is plus 1. And what's the formal charge on that boron? Came in with 3, leaving with 4, minus 1. What if we don't do the extra sharing? Keep it like this. This fluorine 0, 0, 0, and the boron is 0. Because look at boron by itself. How many valence electrons? 3. 1, 2, 3. It makes a bond with each of those, and it has 0 formal charge. But it violates the octet rule, our sacred octet rule that drives everything. Yeah. There's got to be exceptions to everything. I wish there weren't, but there are. But it's the little guys, right? So boron. Boron is a little guy. He's smaller than carbon. So he's not as little as hydrogen and helium. So he wants 6 electrons, not 8. Beryllium is another one. Beryllium's 1 proton smaller than boron. Beryllium also tends to have incomplete octets. So when you're drawing Lewis structures involving some of these smaller ones, boron and beryllium, draw the Lewis structure and then look at the formal charges. And if you can get 0 formal charges by giving incomplete octets to the smaller atoms, it's okay to do that. Any questions?
So, these formal charges and octets more, or which one is more important?
Which one's more important, formal charge or an octet? I think the formal charge would be more important than whether or not it has an octet. But that's really going to come up with these smaller atoms for an incomplete octet. We're also going to see right now that you can have the opposite of an incomplete octet, which is an expanded octet. So for elements in period 3 or larger, we can get more than an octet, because these guys are bigger. So carbon, nitrogen, oxygen, fluorine, they're in period 2. Octet is where they are at. If we go to period 3, we've got phosphorus and sulfur and chlorine, and the bigger ones, they can actually handle more than 8 electrons, and they do sometimes. It's called an expanded octet. They can go 12 or even 14. So let's look at arsenic, pentafluoride, and sulfur hexafluoride. So arsenic, As, pentafluoride. So we're going to stick these fluorines around. So there's 4. And then the 5th one just kind of has to go off at an angle. Total number of valence electrons. There's 5 fluorines. They each have 7. 5 times 7 is 35. Arsenic has 5, so 40. Did I do that right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Like, that's a mess. Yeah, it is. What are the formal charges on these fluorine atoms? 0. Fluorine likes to have one bond, 3 lone pairs. So all of those are 0. What's the formal charge on this arsenic? 0. Can this be okay? Yes, it can. If we try to combine this some other way, we're going to get formal charges. We're going to have a problem. We're actually going to have an expanded octet no matter what, because there's just no way to arrange this with only 8 around. Does this molecule exist? Yes, it does. It's a stable compound. Let's look at sulfur hexafluoride. So sulfur in the middle, and 6 fluorines. So there's 4. We'll stick 1 down here and stick 1 up there. 6 fluorines times 7 is 42, and then sulfur has 6, so 48. I've already got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. There's my 48. All the fluorines have 0 formal charges. They bring in 7 valence electrons. When we divide the bonds in half, they leave with 7 valence electrons. Sulfur brings in 6 valence electrons. We cut all the bonds in half. It leaves with 6 electrons. It has a 0 formal charge. This is called an expanded octet, more than 8. The reason for this is sulfur and arsenic. Arsenic's in period 4, sulfur's in period 3. They have d orbitals available. Those d orbitals are only a little bit higher in energy than the p orbitals, and so they can expand into the d orbitals. And we'll see that our other bonding models explain this better. Any questions? Only period 3 and above. So the little guys sometimes have less than 8. The big guys sometimes have more than 8. Okay, let's look at sulfuric acid. So it's going to be like this. Might start out like that. Number of electrons, sulfur has 6, 4 oxygens each have 6, 2 hydrogens each have 1. We've got, 32? Did we do that right? Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Like, yay! Octets! Beautiful, right? That's not the right structure. Let's look at the formal charges. We don't have to worry about hydrogen. This oxygen has 2 lone pairs, 2 bonds. This oxygen is in the same situation, 2 lone pairs and 2 bonds. That's what oxygen likes. So if we cut these, then oxygen brought in 6 electrons and it takes away 6 electrons, 0 formal charges. What about this oxygen? What's its formal charge? It came in with 6 and it leaves with 7. So it's -1. So this one has a formal charge of -1. And this guy up here has the same situation. Formal charge of -1. Formal charges in this neutral molecule have to add up to 0. What's the formal charge on this sulfur? +2. Because it brought 6 electrons, and if we cut these bonds, it leaves with 4. 6 minus 4 is +2. Sulfur is a big boy. It can expand its octet. It's in period 3. So what we can do when these formal charges say that this oxygen has maybe more electrons than it should, and that this sulfur has fewer electrons than it should. So what we can do is we can make a double bond between this oxygen and this sulfur. So I'm going to take this lone pair that didn't fit up there very well anyway, and I'm going to make that a bond between these two. Does the oxygen still have an octet? It does. And oxygen has to have an octet. It can't expand because it's in period 2. Sulfur's in period 3, and it can expand. So now it's got 10 instead of 8. But sulfur can do that. What happens to our formal charges now? For the oxygen, it's 0. This one's 0 now. What about the sulfur? It's +1. So that's closer to 0. Well, what if we do the same thing with this other oxygen? Right? We take this lone pair and make it a bonding pair. Now this oxygen has a formal charge of 0. The sulfur, it brings in 6 electrons. If we cut all these bonds in half, it leaves with 6 electrons. It has a formal charge of 0. This is the correct Lewis structure for this molecule, an expanded octet. This is something we don't teach you in 3A. So we expand octets to lower the formal charges for period 3 elements. Period 2 elements never, ever have expanded octets. Carbon, nitrogen, oxygen, fluorine, they can't do this. But phosphorus and sulfur can. Any questions?
Would you say that only from
Period 3. So the third row. See, sodium, magnesium, and aluminum, those are metals, and they're going to form ionic compounds. But silicon, phosphorus, sulfur, chlorine, those could do octets, expanded octets, and everything larger could. So let's write the Lewis structure for xenon tetrafluoride. What would you predict the central atom is? Xenon. Fluorine is more electronegative, and so that's most likely going to be terminal. Also, these things tend to be really symmetrical. So we'll put the fluorines around. We count up valence electrons. 4 fluorines, and they each have 7, plus how many valence electrons for xenon? 8. So we've got 28, and 8 is 36. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I had to stick more electrons on there. Where am I going to put them? On xenon. Fluorine's too small. Xenon can expand its octet. So there's 34 and 36. So xenon has an expanded octet. It's cheating, yeah. Greedy. Or you could think of it, you can spin things positive or negative. You could say, well, somebody's got to carry these electrons, and so xenon's the big guy, he's going to take them. Fluorine's got its hands full. Each of these fluorines has a 0 formal charge. What's the formal charge on the xenon? Came in with 8. It leaves with the lone pairs and half of the bonds. Leaves with 8, 0 formal charge. It's okay. Okay, let's do phosphoric acid. This is going to look a lot like sulfuric acid. The phosphorus in the middle and the oxygens around it. And then we're going to put the hydrogens on the oxygens. Four oxygens each have 6 valence electrons. We've got 3 hydrogens, they each have 1 valence electron, and the phosphorus has 5. So 24 and 8, 32. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Looks like a great Lewis structure, right? It's not correct. Formal charges. Oxygen likes to make 2 bonds and have 2 lone pairs, because when it does that, it's going to have a 0 formal charge. So this one, this one, this one, they all have 0 formal charges, right? But what about this guy? Came in with 6, it would leave with 7, that's a -1 formal charge. This phosphorus has a +1 formal charge. Came in with 5, left with 4. So we want oxygen here to have a double bond, so it can have 2 bonds and 2 lone pairs. So we're going to take this pair of electrons there and share it with the phosphorus. So now this has a 0 formal charge, and this phosphorus has a 0 formal charge. Brought 5 electrons, and when things break up, it leaves with 5. Everybody comes out even. That's the ideal. Any questions? The only way you would know to do that is by looking at formal charges. It's so fun.